Hello and welcome to a nostalgic ramble with me. Today we are looking at the department's May 2022 paper 2, question 5.1. Disclaimer is that I did record a video for this question um, probably a month or two ago, and I messed it up so badly that I was just demoralized. I was defeated by myself. Um, And so, yeah, this is me trying to pick myself up and just get back into the groove, hopefully. Apologies for such a long absence. Yeah, I can't promise that I'm going to be more consistent. Um, I have this unfortunate trait that, I'm very disciplined when I am very excited about a project, and that's usually right at the beginning of the project. Um, and so once it's lost its novelty, ah. So sometimes what helps is for me to take a break and then that excitement builds up again. Anyway, wow, story of my life. Let us get into the question, and I'm going to try my best to not mess it up like I did the first time. But yeah, the unfortunate part of that is that, I'm not seeing this question for the first time. Right. In the diagram below, we have the point P with coordinates -7 and 4. It is a point in the Cartesian plane. R is a point on the positive x-axis such that the obtuse angle POR is theta. Okay, and obtuse is telling us that this angle is between 90 degrees and 180 degrees in size. So it was also suggested by the diagram, but yeah, it's always better to have these things confirmed explicitly, right? Not just relying on the diagram. Right. So that tells us that it's in the barring, second quadrant. I mean, we knew that because of the coordinates of P, but yeah, more confirmation of clues is great. Anyway, calculate without using a calculator the length of OP. Okay. So this is our classic Pythagoras on the Cartesian plane because we have the coordinates of P. And how that helps us is we then know that this length over here, if we just drop a perpendicular from P to the x-axis, we know that this length is going to be, oh my goodness, an alarm, my bad. We know that, oh, maybe writing it sideways isn't great. This is 4 units long, right, because of this y coordinate. And then this length over here is 7 units, right, because of the x coordinate, right, 7 units away from the origin. Right, and so we can use Pythagoras to figure out the length of OP. So OP will be equal to the square root of, let's write it out the Pythagoras way. So 4 squared plus 7 squared. But yes, sorry, for those who are wondering, you could just use the distance formula as well, which is Pythagoras in disguise, right? The distance from P to O. But anyway, blah, blah. Right, so this is because Pythag said so. So 4 squared plus 7 squared is equal to OP squared. That is 65, I think. Right. Let's just check. 49 plus 10 is 59 plus 6 is 65. Yes. Right. And so therefore OP will be the positive square root of 65 because we're talking about a distance. So there isn't a possibility that it could be negative square root of 65. Okay, so the length of OP is square root 65 units. So far, so good. And yay, I already filled it in for myself over here. Evidence that I've been here before. Right, calculate, once again, without using a calculator, the value of tan theta, right? The tan ratio of this angle. And we know that on the Cartesian plane, the definition of tan is given as the ratio between the y coordinate and the x coordinate. So tan theta will be equal to y over x, which in this case is no. What did I point at? Y over x, not y over x. Sorry. y coordinate over x coordinate. So positive divided by negative gives us a negative answer of -4/7. Okay. And then this is what really, really just dribbled me and caused me to collapse on the ground. Okay. Because I was trying to be fancy. Anyway, cos of theta minus 180 degrees. Okay. So I'm going to do this in two ways. The first way is using your reduction formulae. I think this is the standard way that is taught. And then I'm going to do it in a way that I find very fun and that kind of reminds us of the relationship of different angles on the Cartesian plane and just to realize that these trig formulas are not just weird esoteric things, but they hold, they make up a little universe. They are rules that work together. Okay, anyway, I'm being very random. Right, so using the reduction formulae, what you would recognize is, okay, we know the reduction formulae for the angle 180 minus theta relative to the trig ratios of theta, right? This is not quite 180 minus theta. It's the other way around. It's like the negated version of this angle. So we're going to use a combination of reduction formulae, right? We're going to use the fact that cos of 180 minus theta is the same as negative cos theta, first of all. And maybe we should shrink you guys. Oh no. Oh no. Okay, it's better. You could even fit on there. Right. So first of all, cos of 180 minus theta is the same as negative cos theta. And maybe let's use a different letter just so, you know, yeah. So cos of 180 minus a is the same as negative cos a. And secondly, cos of negative b is the same as cos of b, right? So how this goes then is cos of theta minus 180 is the same as if we factor out a negative there so that we can switch the difference around, right? So that it looks like, you know, the angle for which we know the rules. I'm just going to shrink this now. Okay, right. And so now, using this second rule over here, we know that cos of negative something, cos of negative, in this case, this is our something, will be equal to cos of that same something, right? So in this case, maybe let's just try to highlight. Okay, I'm going to highlight this as our something. Okay, so that is going to be the same as cos of 180 minus theta. And then we know that cos of 180 minus theta is just the same as minus cos of theta. Okay, so that will be minus cos theta. Okay, so cosine ratio of this guy, but the negative of it. Okay, and how do we work out cosine on the Cartesian plane? We take that to be the x coordinate over the length of the radius. So that'll be negative, well, sorry. Yeah, sorry, I was about to confuse myself. Negative, okay, and then x over r. Okay, so then that ends up being a positive 7 over root 65. Right, and so does it feel a bit weird that this number ends up being a positive number? Because for 2 seconds there, it did make my heart stop. So let's think about, well, what quadrant is this angle in? And this is going to kind of lead nicely into the next approach that I want to show you. So the angle cos, well, no, there's not an angle. This angle, theta minus 180, which quadrant does it lie in? So I'm just gonna quickly visit the next page. So if you have theta and you subtract 180 from it, do you see that it would almost be like if you were to do this, draw 180, okay, this would be you minusing the 180. So the angle goes here first and then it comes back 180. So it's actually then an angle that lies in this fourth quadrant. And using cast, we know that in the fourth quadrant, cos is a positive, gives us positive values, right? Or even if you think about the definition, x over r, in this quadrant, x is positive, r is always positive. So cos of any angle in this quadrant would indeed be a positive number. Okay. I think I'm going to stop this video here because I need to rush somewhere else now. But I'm going to record a part 2 where I will now dive into the alternative approach that you can use for questions like this, where we're not just dealing with straightforward reduction formula type questions. You now need to be a bit more creative. Anyway, let me know what the sound like. Sounds like. This is a new setup that I'm trying, i.e., speaking through my headphones. And I don't know. Let's not make sure. Cheerio. Hello. Yeah, I've now decided that I'm just going to add this part to the end of the previous video. So now it's all going to be one video. So greeting in the middle of a video probably does not make sense now. Anyway, that was me thinking out loud. So we are continuing, right? We are looking at this question where okay, this is more an introduction for myself than for you at this point because I've taken a break and now I need to get back into the question after the break. So we had this line OP, this point P in the second quadrant, and this angle theta, an obtuse angle. And we needed to work out cos of the angle theta minus 180, which is a different angle but slightly related to theta. So we looked at how to calculate the value of this ratio using our knowledge of reduction formulae. But for those of you who are not big on memorizing, um, an alternative way is to kind of do this by inspection. So we started talking about, well, okay, where is this angle, theta minus 180, where is it positioned in the Cartesian plane? So theta minus 180, so theta we already know is this angle over here. So now if I am to minus 180 from theta, okay, we know that theta is smaller than 180, so we're going to end up with a negative angle. And more specifically, we're going to end up with a negative angle in this quadrant, the fourth quadrant. It's not going to come here, right? Because the difference between whatever this angle is and 180 is going to be an acute angle size, right? So think if theta was 150, the difference between 150 and 180 is 30. So anyway, and I think it's also maybe a bit more intuitive. Having drawn this straight line here, we know that this straight line is 180. Okay, so if we started by going in the positive direction, theta degrees, and then we traveled back 180 degrees, okay, we end up somewhere here. So the angle theta minus 180 is now actually just this little piece over here, right? Does that make sense? Okay, so it's pretty much we're saying theta and then minus, so erase this part, this theta part, and then go into the negatives a little bit. So the angle that we're left with is just this part over here, right? So I'm going to erase this. Oh, can I get there? I might be pushing my luck, but I have been known. Oh, what am I doing? Oh, oh, oh! My goodness gracious me. Why am I being terrorized? I did it. I did the thing. Okay, right. So let's close that. So this is our angle. Oh, I need the thing again. Oops. So this is our angle theta minus 180 degrees. Perfect. So we are looking for the cosine ratio of this little angle over here. So the way that you can do that is you try to figure out, well, okay, okay, so let's draw. Let's draw this triangle again. Oops. Okay, so we draw this perpendicular line here and this line over there. Okay, and we know that this is 4 units long and this is 7 units long. Right. So this angle over here is the same in size as this one. We agree? This is because of vertically opposite angles. We've got this straight line, the x-axis, and this straight line that we constructed. So these two are the same in length. So I'm also just not length, in size. Oh, this is why I shouldn't take a break, honestly. Like it's like I just come back and all my language is okay, right. So we can use that to then determine that. Okay, wait, let me try and frame this as correctly as possible. I'm buffering, guys. I'm buffering. I'm coming. I'm coming. So it's almost like you can imagine we can take this triangle and then this is where I really wish I could have more powerful visuals, animations in particular. What I want to do is I want you to imagine me taking this triangle and then, ooh, and then bringing it here. This is not going to do what I wanted to do, right? So that would mean kind of, is that a reflection? It's not a reflection, it's a rotation. So it would be like taking this guy, okay, and rotating him once. Oh my gosh, not you, just you. Okay, you rotate him once like this, and then again like that. Okay, and let's actually be more specific. So this is the angle that we care about over here, all right? And I'm also going to hold on to the dimension. So we said that this is 4 and this is 7. So imagine taking this triangle and then rotating it by 90 degrees. So that would take it to this quadrant over here. And then rotating it again into the fourth quadrant, right? So that it ends up here. Do you see what I'm saying? I hope you see what I'm saying. So this is the relationship between this triangle here and this triangle here. So the angle is the same, the 90 is there, and then obviously third angle, those would be the same, right? So these triangles are similar, okay? At the very least, they're similar. We're gonna make them congruent now because that's what we really care about, right? So because they're similar, if I decide that I want to make this length the square root of 65, then this will be 4 and this will be 7. Okay, so pretty much I'm saying take this exact triangle, rotate it once so that it becomes like this over here, rotate it again so that it ends up like this over here. These angles are exactly the same, the 90 is the same, third angle is the same, and I am choosing the length to be the same as well. As we know, trig is all about similar triangles, and that's why we talk more about ratios than we talk about exact lengths, right? It doesn't actually matter whether this is square root of 65 or double that or quadruple that. These dimensions will also just double and quadruple, etc. And the trig ratios will then remain the same, no matter how big or small the triangle is. Um, right. So that would then mean, first of all, let's get rid of little upside down triangle. That this point over here would have the coordinates +7 and -4. Okay. And so the cosine ratio of this angle that we are so interested in would be the x coordinate, which is 7, divided by the length of the radius, which is √65. So it's a bit of an interesting way to think about how to figure out the trig ratios of related angles on the Cartesian plane. But I enjoy it so much because it forces you to think about the relationship between the different angles that you are dealing with. So given the ratios of this angle, how is this different angle related to that angle? You know? So yeah, every time I try to do a video touching on this way of doing trig, I feel like I get slightly better at explaining it. But I will recommend, if you can find the YouTube series online, I think I'll also try to link it, that talks about circulometry as a starting point for trigonometry. So this idea that trig actually it makes more sense to begin trig on the Cartesian plane. That is where it is at its most complete, and then go to the triangles, the SOHCAHTOA, etc. And we typically do it the other way around. Anyway, but I just enjoyed that perspective on trigonometry so much, and I feel like it gave me a deeper understanding of what trig is actually about, and to move away from just looking at it as a bunch of formulas that I must just memorize by rote. Anyway, that is my ramble for the day done. Thanks for tuning in. Catch you next time for another ramble.